now we're going to look at thick wall pressure vessels. And to start off, we're going to start off with the same concept for longitudinal stress. Right, you have a pressure on the inside. We have this area is where that pressure is trying to push out. Right, so we're looking at longitudinal stress. So it's trying to push out the vessel in that direction. And we must have the force in the material that results from the stress that counteracts that force. So we know that this area here is equal to pi r squared, ri, right? And what ri is, we have ri as the inside and ro as the outer, right? So because it's a thick wall pressure vessel, we need to consider now the thickness of it, right? Consider the inside, internal and out, external. So just like we had before, we had pressure by pi ri squared, right? So that's the force that pushes out is equal to longitudinal stress pi. Now we have to consider now the outer diameter and inner diameter, so separate diameters. Right, so what this is here really is the area pi r o squared minus the area of the internal pi r squared. Right, so that is this area here, right, of the annulus ring. Right, so when we do that, we could solve for longitudinal stress as PRI squared on the difference of the squares of the two internal and outer radius. Right, so this is the longitudinal stress. Right, but as you would see, as we go on in this section here, we don't really focus much on the longitudinal stress as we did with the thin wall. And that's because now, unlike thin wall, we need to consider that radial stress, or that stress in the radial direction. Alright, so before, if we took an element, and we had sigma hoop, right, and we said that the sigma r was negligible because it was too thin to consider. But now that we need to consider it. Alright, so that is how that's our stress element. Now, I just want to draw this over again, just to highlight something. Right? If we have that section, and this is a bit exaggerated here, and we were to take a slice of it, right? So let's just take a right. So if you were to draw some forces on this, you will have sigma being applied in that direction. Right? We say that we have sigma r here in that direction, but we're saying that the sigma r changes as you move out. Right? So along this dotted line here, or this radius, the sigma hoop is one value, but we have one value for sigma r here, and at a higher radius we have a different value. So we say that sigma r changes. And how we capture that, when we say sigma r, what it was before, as below, plus now the change in sigma r with respect to the radius, because we're saying it changes as you move out, times that change in radius. Right, so let's go over that again. We say that sigma r changes as you move out to different radii. Right? We're looking at one radius here, so therefore the sigma h on one side equal to the sigma h on the next side. However, we have one radius here, and then we have a larger radius here. So the sigma r here would be sigma r, or whatever value, the sigma r. And over here now, we would have a different value. And we're seeing a different value be sigma r, what it was originally, plus the change in the stress. Right, so this is like but as you move up, that sigma r is going to be changing with respect to the radius. Right, so that's d sigma over dr times now the distance we move. Right, so we could just say that this distance here we move is dr. Right, now if you were to take a force balance of this, on this sector or element, I should say. Alright, so let's just say we resolve the forces. Right, which we're not going to do. We would end up with what we call Lami's equations. Alright, so there's a bunch of maths that I don't want to get into. Alright, and those equations are sigma r is a minus b on r squared, and sigma hoop is a plus b on r squared. So these here is what I call Lami's equations. Right, and then we're gonna show now how we're gonna use this equation to calculate stress sigma h. You notice we have a and b, though, so it's not a normal formula where you have like PD on 2t. Right? You have constants a and b, and these values of a and b depends on the boundary conditions of the problem. Right? So we're gonna take a look at that in the next short video.